We know that cover crops have many benefits. It is now established that this practice fosters biodiversity above and below grounds to build up sustainability and resilience of our ecosystems. One of the main benefits, for instance, is that it provides forage for pollinator conservation and pollination of our crops. It provides the environment necessary to break pest and disease cycle and decrease weed pressure. Most importantly, it can also foster soil health through living roots in the system, keeping soil covered, and residue retention. This helps improve soil structure, fertility, and eventually the need for inputs. Ultimately, cover crops are a critical tool to decrease our need for inputs while regenerating the resources and landscape upon which we depend.
In California's watertight environment, though, the use of cover crops has always been a concern because of their perceived additional water use. From 2016 through 2019, a group of researchers from the University of California at Davis conducted extensive work to add information to the question of cover crop water use. In summary, our findings from this work were that there were not significant differences in soil moisture between cover-cropped and control fields, either throughout or at the end of the winter seasons. Combining reduced disturbance tillage, winter cover crops, and surface residue preservation led to higher soil water contents than bare soil surface non-cover crop conditions. And finally, we express caution about the use of satellite remote sensing to characterize soil water dynamics during the winter cover cropping growing period.
This work was done to answer a really important question around the water impacts of cover cropping, which is a really important sustainable practice. They've gained a lot of attention in recent years, but their adoption remains very low in California. The number might hover around 5% of farmland is planted with a cover crop. And part of that reason is the unknown. How much water do they use? And can I, as a farmer, afford to give them that water? So we wanted to answer that question. There was a very clear knowledge gap in water use by cover crops in California, and that's what our research sought to do, was to fill that knowledge gap. The research was really focused on trying to capture the diversity of agricultural operations within California's Central Valley and understand how cover cropping on those farms affected the water balance. So first, we had to identify partner farmers and set up experimental plots on their land. And we found 10 of those. And they covered tomato operations and almond operations. And they went all the way from Chico in the north down to Arvin in the south. And our goal was to capture a climate variability that growers within the Central Valley can experience. So really wet winters down to really dry. Within that pool of farmers, we wanted to capture variability in cover cropping practice. People who had never cover cropped before, and those who had been doing it for many decades. On those farms, we designed comparative plots. So we took their area with a cover crop and set a piece aside to act as a control without a cover crop at all. On each of these farms, we collected data to describe cover crop water use. That included soil moisture and evapotranspiration. So we collected data at different intervals. We collected soil moisture samples once or twice a season, and then we collected soil moisture readings approximately once a week at each of these sites. And we did that work for 3 years. In addition, we tried to collect information about evapotranspiration. Now, you can't measure that directly, so we instrumented 2 of these fields very heavily and captured data on all of the components of the energy balance so that we could then calculate evapotranspiration. So the data analysis was a very challenging part of this experiment because we had a really diverse data set that had some inconsistencies in time and space, and there was a lot of variability between all of our fields because our goal was to really capture diversity. So to analyze this data, first we had to collect it by hand, and that involved many project partners throughout the whole state. We then had to clean the data and digitize it. So that involved countless hours of internship help, just getting data from the pen and paper onto the computer. Then we had to clean it and make sure that all of the numbers made sense. And then I really got to work experimenting with how to look at such a diverse data set. Tens of thousands of data points, all trying to answer the same question. So what I ended up doing was calculating some new metrics for cover crop water use. The first one was just statistical differences. How often was soil moisture different between a cover crop field or bare ground? The second thing we looked at was a cover crop ratio. So I divided soil moisture from a field with cover crops by a field with bare ground. And that gave us a number that was very simple to communicate. A ratio greater than 1 means there's more water on a cover crop field. The last thing we did was we measured and calculated fractional soil moisture. So we figured out when a field was saturated and then how much of that water was left over at the end of the winter cover crop season. Once we did that for every field, we then aggregated that data across systems and across all of the 10 fields to try to find trends and directions. Our main finding was that soil moisture generally did not differ between fields with or without a winter cover crop during the winter season. When we did see differences, they were very concentrated in the top meter of soil, and generally they were on farms that had already been cover cropping for many years and sometimes decades. From an evapotranspiration perspective, our finding was that generally cover crops added very little evapotranspiration demand to a field. In fact, the majority of the water lost on a field comes from soil evaporation. And the actual amount of water that cover crops were evapotranspiring on our two fields amounted to less than an inch of water, which is small in the scheme of an irrigation budget for a farm and is really a rounding error when you think about major water budgets in the valley. So our data and our work gives some of the first numbers on actual cover crop water demands within California's specialty crop systems, and it provides a starting point for the regulatory agencies and the groups who are implementing SGMA to think about this practice in a new way with data that backs up and supports its incorporation into groundwater sustainability plans. So we learned from some of our partner farmers that there's a method that some groundwater sustainability agencies are using to estimate agricultural water demand. And that is called remote sensing, and it's where you take an image and then calculate crop water demand from those pixels. There's a concern that photos taken during the winter time might capture cover crops and overestimate their water use because these algorithms might not have cover crop data incorporated into them. So we've found that their water use is not instinctual. It's somewhat counterintuitive how little water use we have found them to be using. So we want to really encourage groundwater sustainability agencies to think through the nuance of these models and understand that cover crops are a special practice that can't necessarily be generalized by one crop coefficient. They're a diverse group of plants that have really diverse impacts on an agricultural farm's, on an agricultural operation's water use. So the entire issue of SGMA implementation needs to consider cover crops specifically because we don't want this sustainable practice to be discouraged by water accounting. it's all working towards the same goal. We really found that cover crops can fit into management plans without increasing water use and improving soil structures and all the many benefits of cover crops that we know to be true. So there is a potential that this could be overlooked if it's not brought to a GSA's attention and to their modeling group's attention.
Our research group also did work on cover crop water use in the National Research Initiative, or NRI, project field in Five Points, California.
Yeah, so the NRI project located in Five Points, California is a long-term research study, and the design of the study is to look at the impact of conservation agricultural practices, and specifically we were looking at the effect of reduced disturbance tillage and winter cover cropping on soil water content, and trying to look at the combination of these two practices. So in order to collect data on the soil water impact of reduced disturbance tillage and winter cover cropping, we took soil neutron probe readings in the different treatment plots throughout 3 years. So we did from 2016 to 2017, 2017 to 2018, and 2018 to 2019, and specifically between January and March of each of those years to understand how the soil water fluxes change based on the different treatments in the soil. So our findings show that on average throughout the 3 years and the 4 different treatments, the soil water content of the treatments that are reduced disturbance tillage and winter cover crops were actually the highest amongst the 4 different treatments. And this was particularly seen in the drought year, which was the 2017 to 2018, where we got just over an inch of rain throughout the January to March winter cover crop season. And so this actually showed that this treatment had the most soil water, and comparing the 4 treatments, that soil water was not. Basically, the combination of reduced disturbance tillage with winter cover cropping did not deplete the soil water content of our soils, and that was a big concern amongst growers and farmers who were hesitant about adopting these conservation agricultural practices in the state of California, where drought and water availability and supply is such a concern. This work is super important, as that this research took place in the heat of the Central Valley and the center of it basically having water and drought concerns. And so farmers are hesitant, of course, to adopt and plant winter cover crops with the thought that these cover crops would use soil water and that would then deplete their profile. However, we actually found that the combination of reduced disturbance tillage with winter cover crops led to more soil water, because we were capturing more of the water when it did fall from the sky, so trying to have the soil as a storage water bank, and also reducing the evaporation loss from soil due to the cooler soil temperatures, and the ability to keep soil organic matter by reducing our disturbance tillage, by using reduced disturbance tillage and trying to maintain that soil water. So actually we found that those plots had the most soil water content, which was contradictory to what we would have thought before. At this site, we looked at also the influence of reduced disturbance tillage and found that by adding this reduced disturbance tillage, we actually save more water in the soil profile and have seen more water besides just breaking even, which is what the other sites have shown. So I think in terms of looking at drought mitigation and adaptation strategies in the state of California, and looking to which conservation agricultural practices are best fit in the growing conditions and the climate, cover crops, winter cover crops, can really help us create a water bank in the soil. So really treating the soil as a bank of water, and it's almost like an insurance against the drought. And being able to have extra water being infiltrated down in and then also held in the soil profile during the growing season will help farmers not only to add organic material to their soils, increase their carbon, but also to preserve their water in the soil, despite the use of water that the cover crops may have.
The findings of our group's research on cover crop water use have particular importance today in light of the implementation of SGMA, the Sustainable Groundwater Management Act, that mandates sustainable groundwater management.
Okay, the regulatory aspects of the Sustainable Groundwater Management Act states that every groundwater basin has to come to a balance between the natural recharge and the amount of water that is pumped out of the aquifer. In terms of sigma, this findings of the winter cover cropping are important. First of all, because I think there's a misconception, a general misconception about the amount of water that is used by different cropping system, whether is clean cultivated or cover crop. And secondly, most of the time for sigma regulation, satellite remote sensing technique are used to estimate the consumptive water use. Now, satellite has a lot of capacity, a lot of benefit, but there are a lot of things that are prevented to evaporate, like it happens in the bare ground, thanks to this layer of canopy. It's true the cover crop loses some water, but the net benefit of what it gains and what it loses is probably profitable, and more water becomes available to the plants or to the trees or anything that requires water for its life cycle. Well, first of all, we cover several climatic conditions where important relevant crops are grown in California. So we conducted a very similar research in several climatic conditions that have different environmental growing conditions like rain, temperature, and we wanted to see what was the basically the net gain or loss of having a cover crop onto the ground with respect to the bare ground, clean cultivated soil. And the importance of that is that probably the benefit, the amount of benefit of cover cropping is location specific and crop specific, so has to be evaluated very well in detail and not generalized for the whole Central Valley. So the importance of that survey is covering several cropping systems and several climatic and environmental growing conditions. Well, in terms of water, we figured it out that the presence of cover crop allows the soil to infiltrate a little bit more water, to store water that later on is available to plant for growth and production. And overall, we found that winter cover cropped soil does not lose more water than bare ground. Bare ground loses water, but the cover crop is considered like an active vegetation surface, but stores more water, loses some of that water, but the net benefit of it is probably more positive than negative to growers in the different climatic conditions of California. I think it's important because there are water productivity aspect of winter cover cropping and also sustainability, environmental sustainability aspect. So the soil with a cover crop is in a better health conditions than a soil that is tilled and worked. But overall, I think we tend to recreate what the nature would do if tillage was not invented, or if tillage was not conducted by growers. So what you see in the ground is either native vegetation growing up out of the winter rainfall storage, and this recreates what nature will do normally. The relevance of that is that we tend to have better growing condition for the plants, a better fertility in the soil, and regeneration of the soil cycle and nutrient cycle also, when we come to an orchard level or field level or farm level. And one of these things is the amount of soil moisture that is stored and infiltrated into the soil. The amount of water that is used by the crop is sometimes there's a lot of inaccuracy, a lot of errors in the technique for estimation. So research like the one that we conducted are specifically aimed to provide science-based information on what happens in a cropping system that has as a cover crop with respect to a cropping system that has a clean cultivated soil. And these are detailed information about soil water dynamics and consumptive water use that normally occur during the period of active growing vegetation and during the period of dead vegetation that stays onto the row middle and performs function of mulching and protection from soil water losses. Okay, local GSA have to balance the amount of water that is consumptively used by crop area relative to the groundwater recharge. Now, most likely groundwater recharge is facilitated with winter cover cropping with respect to a clean cultivated soil, but also the amount of consumptive water used during winter time, during the period of active growing vegetation in cover crop area, is very, very little with respect to the amount of water that gets infiltrated into the soil. Well, this is a controversial aspect because the state tend to incentivize and provide financial incentive to growers to grow cover crop for soil health purposes, but at the same time, growers that happen to be in the common area of groundwater sustainability agencies will be probably penalized by this idea that cover crops takes more water than non-cover crop. And so there will be a balance, but I've seen a lot of growers that, actively growing cover crop during the winter and mow the cover crop and disc the cover crop when, it comes the time of active bud break and start of the vegetation of the main cash crop. I think there will be a balance between the two, but this is a controversial aspect that we, as University of California, intend to clarify, providing more detailed science-based information of the soil-water dynamic of winter cover cropping. There are misconception and lack of sufficient information about the consumptive water use of a cover crop system and of a clean cultivated. The old-fashioned way of considering things estimates that there's less water use in a bare ground than in a cover crop ground, and during our research project we found exactly the opposite. A cover crop can work under Sigma if it's well managed and well regulated, because I think our role is to provide sufficient information to groundwater management agencies about the proper timing and the proper timing for establishing cover crop and the proper timing for terminating the cover crop in order to maximize the benefit in terms of water infiltration, water storage, and reducing the unbeneficial consumptive water use. And so timing is important here. And so providing sufficient information to regulator and to water resource planners and managers is pretty important and will allow probably growers to practice the cover cropping in a proper setting. The research is at its final and conclusive stage, and the main findings is that cover cropping alone is one thing, but jointly with other ground management practices can even maximize benefit, like reduced tillage or minimum tillage coupled with cover cropping will allow to maximize the net benefit in terms of soil water dynamics.
Related work being conducted by Dr. Daniele Zaccaria is shedding light on other aspects of cover cropping systems that may be influenced by cover crops.
The aspects that I'm investigating in several locations, in several nut crop orchards, concern the radiative effect of cover cropping and how these properties might impact the water productivity. In simple terms, cover crop is a green vegetation during the active growing period and reflects part of the incoming solar radiation in different direction, and part of that radiation can be recaptured by the lower part of the tree canopy. That recapture provides more energy to the plant, probably better soil health and nutrient dynamics, and so a plant will benefit from this additional solar radiation because it will mobilize more nutrient, more water, and at the end of the story will probably have more yield and better crop quality. This is what we found in several pistachio orchards, and we are extending the investigation in wine grapes and in almonds production orchard to see the specific effect of winter cover cropping and inactive vegetation residue over the course of the growing season in terms of water productivity. So more crop per drop of water. And again, we're still talking about cover cropping that grows on winter rainfall, not on irrigation water applied to the ground.
As we have seen, some of the benefits related with winter cover crops in California are related to soil health. So for instance, they may improve soil infiltration, they also improve soil water retention, and increase organic soil matter. Also, some of the benefits are related with their hydrologic feasibility. What does that mean? That a winter cover crop compared with a bare ground soil, they may use about the same water. Why is that? Because cover crops, they may help to infiltrate water. Cover crops use water, yes, but they also infiltrate and retain water compared to a bare ground fallow field that they may just run off or evaporate a lot of water. Some of the nuances related with cover crops are the cover crop species. It depends on the cover crop mix or if it is native vegetation. They also relate with the tillage practice. This is very important because these may improve or enhance the benefits of cover crops. They also might be dependent on the management practices, meaning that for how long cover crops have been practiced in a given field. And finally, they might be also dependent on climate and soil type. It will be dependent on the rainfall and temperature pattern, as well as the underneath ground. Because of all these nuances, cover crops must be monitored on the ground. As we have seen, there are very promising methods to estimate how much water crops use from satellite information. However, specifically for cover crops, these estimates should be monitored, calibrated, and validated on the ground. If we don't do this, we may overestimate or underestimate. Also, from a bird's eye view, meaning from the satellite, not all green fields can be counted towards irrigation from surface water or groundwater. Specifically, cover crops, they are rain-fed crops, meaning that the water that they use comes from the rain. All of these nuances should be considered when we are estimating water use for cover crops.
In summary now, our findings from several years of detailed farm and research station studies indicate the following impacts of winter cover cropping on soil water in Central Valley croplands. Generally, there were not significant differences in soil moisture between cover cropped and control fields, either throughout or at the end of the winter seasons. Combining reduced disturbance tillage, winter cover crops, and surface residue preservation led to higher soil water contents than bare surface non-cover cropped conditions. Explanations for these findings are complex and involve the following factors. 1. Generally low evapotranspiration demand during the winter period in the Central Valley. 2. shading and cooling of the soil surface by cover crops and surface residue, resulting in lower soil water evaporation. 3. Overall improved soil health in cover cropped and reduced disturbance systems, leading to increased soil aggregation, water infiltration, and storage. And finally, because of this complexity, we express caution about the use of satellite remote sensing to characterize soil water dynamics during the winter cover crop growing period in California's Central Valley.